TADS seminar this week. We're very happy to have Variyam giving a talk today. So Vinod is currently a faculty of computer science at University of Nebraska-Lincoln. And he primarily works in foundational aspects of computer science. He made several significant contributions in complexity theory, namely in circuit complexity, space-bounded computation, randomization, and Kolmogorov complexity. And of late, Vinod has been looking at some problems related to large-scale data analysis and machine learning from an algorithmic and complexity viewpoint. Okay, so Vinod, we're glad to have here.
Yeah, thank you, Pawan, for the introduction.
And I would like to just add one more thing. Vinod is one of the key members of the Tripods grant. Yeah, I just would like to add that. Yeah. Okay, Vinod. Yeah.
Thank you. Yep. Okay. Thanks for giving me an opportunity here. And so I was just mentioning a few minutes back, this is the first talk in this area I'm giving. So, and the world expert is listening, so I'm a little nervous. So, but let's start. So this is a joint work with Arnab Bhattacharya from NUS and Sutanu Gayan, who's currently at NUS, and Sharavanan and Ashwin. And this work started when I was at sabbatical in NUS last year. So, and it's supported by NSF award, including our tripods. And this just appeared in ICML 2020. So let me start with what we are trying to do here. The main contribution is that we present an algorithm with provable sample and time complexity guarantees for the problem of identification of interventional distributions in causal diagrams from observable data. And of course, there are a lot of words here, which is I need to explain. So to distinguish from what the earlier work made tremendous progress on isolating conditions under which interventions can be identified from observable data, but it assumes perfect probability scenario. In particular, it assumes unbounded number of samples. So the main contribution is to actually make one of the work in a more complexity theoretic or algorithmic setting where we prove provable guarantees on time and sample complexity. Okay, so that's the main contribution in this work. Now here is the theorem, which as you can see, a lot of details to be filled in here. So my main purpose will be to explain this theorem with making clear all these notations and notions here. So the theorem is essentially that it's an algorithm. We give an algorithm which takes a causal graph with n observable variables and another variable x which you want to intervene. And when you intervene that, you get what we call interventional distribution, and that variable should meet Tian-Pearl criteria, which I'll explain. And if the algorithm will take such an input, and it's going to output a distribution or some representation of the distribution p hat, and the guarantee is that the statistical distance between p hat and p sub x, which is the interventional distribution, is small. So we are giving an algorithm which which learns a distribution which is close to the interventional distribution. And that representation has the property that you can evaluate and also sample very efficiently. And moreover, the algorithm has bounded complexities, and there is a lot of other parameters here. But right now, I'll just say that it takes approximately n by epsilon square samples and runs in n square by epsilon square time. Okay, so that's the main theorem. And of course, there are a lot of notions here which I need to go through. So the purpose of this talk is actually to explain what this theorem means, and I only have one slide on and the idea of how the theorem is proved, but hopefully I can at least make a case for this theorem. So let me start with basic notions here. So we'll start with Bayes nets. They are probabilistic graphical models for describing high dimensional distributions with dependencies, and has many applications in statistics, machine learning, etc., etc. So it is formally, you can think of it as two components here. One is a DAG, is a directed acyclic graph VE, where V is a set of nodes, E is a set of edges, where V represents a set of random variables and E describes dependencies between these variables. And to describe a probability distribution on V, what we do is to give what is known as a conditional probability table, which means that for every variable X, and for every setting of its parents in this graph, you prescribe a probability distribution. So it's for every variable there is and every setting of its parents there is a distribution. Okay, so we'll go through an example, and those who have taken machine learning will know these much without much difficulty. Okay, so once it's described, what we can do is that we can exactly describe a probability distribution or joint probability distribution on this set of variables. And in particular, if I take let's say that these variables are topologically ordered in the DAG, then you can the probability of any particular sample point x1 to xn is given by this factorization. And the main point to notice here is that xi is only going to depend on its values of its parents. Okay, so therefore you can actually compute these probabilities. So good thing is that if I have this graph which has some restrictions, such as the in degrees limited or things like that, then it gives a succinct way of representing high dimensional distribution. Notice that even if xi takes binary values, this distribution is on 2 to the n sample points. So if you know additional information about this distribution, such as dependencies, you can actually represent them much more succinctly. So here is a typical example of a Bayes net here. So here is the three variables here. It's rain, sprinkler, and grass wet, and the edges shows the dependencies. And you can see that on the sides there are these probability tables. For example, rain has a table. Rain doesn't have any incoming edges, so it doesn't have any parents. Therefore, you can specify it by just giving probabilities for either true or false. And if you look at sprinkler, it has one parent, rain. So for each of the setting of the parents, rain is false or true, it has a table. And similarly, grass wet actually has two parents, and it gives a table for each of the possible settings of its parents. Excuse me. So given that, so suppose you wanted to compute the probability that of the event that it doesn't rain, and it's so not R means it's rain is false, not sprinkler, and the grass is wet. And you can compute this probability by just doing that factorization I mentioned. So you start with the rain probability that rain is false times probability that sprinkler is false conditioned on rain is false times probability that grass is wet conditioned on sprinkler is false and rain is false. And by looking at this table, you get the probability of 0.18. So that's an example, of a Bayes net. But in many real life situations, actually, we would like to understand the distribution of variables such as, say, rain here or grass wet, if certain other variables are intervened and forcefully set to certain value. Say, for example, so I wanted to know the probability of rain for, if the sprinkler is set to false. So if you go back to this picture, so let's say that sprinkler is set to false. What is the probability of rain? Okay, so just for the fun, just to make a point here. So that is denoted by the following. That is, we would like to know probability of R. This is called the do operation, forcefully setting S to F. So one would ask, why do we need this additional notation here? But let's give me a moment. I'll explain why we need that. Okay, so that's what we would like to know. So what is that? If you look at the previous picture, if you take the sprinkler set to false, forcefully, it shouldn't affect the rain. I mean, rain should be completely unaffected by whether you set sprinkler forcefully to false. So intuitively, we want this value, that probability rain, conditioned on, okay, I should have that, not conditioned on, if you do, it should be same as probability of rain, which is equal to 0.2. So that's what our intuitive meaning should of the intervention should capture. And the crucial observation is that it is actually different from conditioning. So from the base nets, you can actually compute what is the probability of rain conditioned on false. Sprinkler takes false value. Sprinkler is set to false. So that this gives to 0.38. So for example, you can, here you have the calculation here, probability R set to R is true when sprinkler is false. You can do the Bayes theorem, and you can compute this probability and you get exactly 0.38. So notice that that's very crucially different from what we want to achieve. We wanted that if you forcefully set your sprinkler to false, it shouldn't affect the rain. Rain should still have a probability of 0.2. Okay, so that's what we wanted to capture here in this interventional situation. And the way to do that is to actually consider this, call it the truncated base net, so to say. So what we did is we took off the incoming edges to sprinkler from the previous base net, and we set sprinkler to false. So several of the tables have gone. So now we have a different table which is derived from the other table, and you get a base net. Now you can actually analyze this probability of certain variable taking a value conditioned on forcing sprinkler to false. For example, you can compute probability of the grass is wet conditioned on, or not conditioned, I should say, forcing sprinkler to false. So you can by just looking at the factorization of from this particular truncated base net. Okay, so you'll get 0.518. Okay, so because you can see that is nothing but probability of grass wet conditioned on rain times probability of rain, etc. Okay, so you can, because I'm looking at that truncated table for the sprinkler is only have value f. Okay? And you can do this calculation and you'll get 0.518. So that's the basic idea of interventional distributions. So far everything looks good. It's not that difficult from different that difficult from given a base net, you can actually compute these interventional distribution. But this is the case when all the variables in the base nets are observables, and as I mentioned, you can do these computations. But in the real life situations, there are variables that are hidden and that cannot be observed. Okay, and the challenge is to now compute the interventional distribution from the distribution on the observable variables. Okay, so that brings us to this causal base net. So let me give some formal definition here, and then we'll go run through an example. Okay, so in this case, we have a DAG. It's like a base net, except that we have a set of hidden variables u, and since they are hidden, they can affect other observable variables, and they are stand by itself independent in the sense that there is no incoming edges to u. And in this, again, what is given to you, or for the definitional purposes, there is, for every variable, and every setting of its parents, including the hidden variables, there is a distribution given to you, okay? And also the distribution on U also is there. And if in this situation, you can define the interventional distribution for an observable variable and a particular setting of the observable variable x, you can define the interventional distribution P sub x of V or PV of do x, and is given by this truncated factorization. Again, it's given by this particular expression here. So what we did is that essentially, if you notice, we took away x out of the factorization because x is set to that particular value, and we marginalized u. So it is summit over all possible u's, etc. So that's the way we define this interventional distribution. One thing to note is that this is the definition, but we don't know what PU is going to be, because that's not something which you can see. And this, the one here I defined is only for one single variable x, intervention on single variable, and that they're called atomic intervention. But it's straightforward to define these things for set of variables. So, but I will not go into it because for this purpose, for our work, we only consider single variable. Okay, so here is an example. So we have three variables x, y, z, and those are the observable variables, and u is the hidden variable. And we have given all these probabilities for each of. Okay, so yeah, that's right. So that's what is on the right side you have, and then you can define probability of y, z, do x to be this particular marginalized factored expression here. Okay. So I wanted to ask so far any questions, or I know that it is difficult to ask questions. You have to unmute and but please interrupt me if you have questions.
Okay. Just a question about the ordering. Is that unique, or is that could be multiple different kind of decomposition of the ordering?
You can have multiple. Any topological ordering will give a factorization. Make sense?
Yeah, just okay. I will see what you do with it. But if they're not unique, then are they gonna give you consistent answers, or when you?
Yeah. Okay. So so it is going to give consistent answers. It is so you're asking that in the general basenet case, there are various topological ordering, and any of that ordering will give you the same probability. Okay.
Thanks.
Yeah. So so the main question is of identifiability of this interventional distribution. So what that means is the following. So we have given a graph. Let's say there is a DAG, which is, say, suppose you know this DAG, and it has set of observable variables v and hidden variables u, and given a variable, and you wanted to express the probability of y if you intervene on x, and you can only see the probabilities on the observable variable. So is there a way you can express this quantity using only observable variable? So this is the identifiability question, and there is a lot of work. I mean, I only started looking at this very recently. So, but as from my perspective, a lot of work by Pearl and Julia Pearl and his collaborators trying to identify to address this particular problem. Very relevant, very interesting problem, very well motivated problem. Okay, so that's the identifiability question, and let's run through some examples to understand this. Why is it an interesting question? So, for example, let's consider this particular CBN. So we have two variables, x and y, and you have an observable variable x and y, and then there is hidden variable u. So the question is y to x identifiable? So that is, given observations from pxy, can you uniquely express probability of y do x? And you can what I'm going to show you is the answer is no. So how do I show something is not possible in this situation? So what you do is you construct two distributions P and Q, so that the observable part of these two distributions, so P and Q, which is consistent with that particular DAG I showed you, and but the observable part are the same, but then when you intervene, these give different answers. So therefore there is no unique. So by observing only xy, you cannot give a unique interventional distribution. So therefore we conclude that that's not possible. Okay, so here is the example where there are two distribution P and Q for which Pxy and Qxy are the same, but when I intervene on x and set it to 0, they're different. Okay, so for in this example, you can take u to be let's say Bernoulli half. So 1, 0, and true or false. It takes both of them takes all the variables takes binary values. So u is 0 with probability half, 1 with probability half. X is just copies u, and y we make for P, we make y to be 0. For Q, we'll make y to be XOR of x and u. Okay, so it's kind of so you can check very easily Pxy equal to Qxy. You can set x equal to 0, y equal to 0. And you can see that Px equal to 0, y equal to 0 in both cases is half. Px equal to 0, Px equal to, so x equal to 0 and y equal to 1 doesn't happen because y is set to 0 in P, as well as y is nothing but XOR of x and u. So when x and u takes different same value, XOR of x and u. So you can calculate this. So I should have done that.
So, Vinod,
yeah.
So when you say x is u, so what does it mean? It's like an independent copy of u, or is it like?
No, it copies. So the table is exactly u. In other words, whenever u, so for example, let's say u takes value true, then x cannot take value false.
Okay, it's exactly the same.
It's exactly the same. Yeah. Yeah, so I had the calculation here, but you can verify that they are the same. Pxy and Qxy are the same. But if I intervene on x and set it to 0, you can see that y cannot, P always y equal to 0. But when so y equal to 1 is probability 0. But in the second distribution, when I set x equal to 0, it is actually basically copies u. So it has a half probability of taking 1. Okay, so that's the example. Okay, so that's an example where you cannot uniquely determine the interventional distribution from just the observational distribution. On the other hand, let me show you another example here. So here what we did is we had introduced a variable z, which it's called a mediator variable. And then now if you wanted to ask this question is when I said x to x can I identify, you know, the probability of y? Okay, so typically one y is z, but let's, I mean, you wanted to ask in this particular case, I'm asking whether what is the effect of intervention of x on y? And this is actually turns out to be yes, and you can write down this expression here: free y do x equal to this quantity here. Now you can see that u is gone. There is no u here, right? So therefore this is identifiable. Now, how did this expression come up? It's a very clever manipulation. You can work out yourself. Each time I try to work out, I get stuck. So I'm not trying to do it here, but it is not trivial, but it is probably one of the very useful exercise to do it. So, so significant research has gone into isolating graph properties of the underlying DAGs for which interventions can be identified from the distributions on the observable. So the question was, what kind of properties my DAG should satisfy so that interventions is identifiable? And so what I'm going to talk about is this particular criteria, which I call Tian-Pearl criteria, which characterizes identifiability of atomic interventions. Okay, so it's completely characterizes identifiability of atomic intervention. And Tian is listening. So, and I would wanted to also add that this is Tian-Pearl paper is one of the papers I like the best in this topic. Okay, so what is Tian-Pearl criteria? So okay, so you can all unmute and give me a big love for the slide. Okay, so I'll tell you when. So in this, it's standard to actually assume that these hidden variables are actually only depending on 2. Okay, so it has exactly 2 children. So it is widely used assumption. And one thing it's not yet clear to me is it without loss of generality or not, but in any way it makes a lot of sense to do that, and it is assumed. So if that is the case, what we can do is that we can hide the hidden variables from this graph. Okay, so by just connecting its 2 children by just a bidirected edges, and we can call this graph. Now the graph, initially with u we started with a DAG. Now you take away all this hidden variable and just put a directed bidirected edge between them. So you get actually a mixed graph. Some of the edges are directed, some of the edges are bidirected. Okay, so once we have a set of bidirected edges, you can actually look at the graph and its connected component. Now, a C component is the connected components of observable vertices in the graph when you restrict to only bidirected edges. So this is one notation I need, or one notion, and I think it's very, very important notion, at least when I trying to understand this, played a key role in this. So I will come back to the with an example here, but that's a Z component. So we have a graph now. We have taken out unobserved variables or hidden variables and connected with bidirected edges. Now I'm only looking at the graph with the bidirected edges and trying to look at the connected components of that graph, and the maximal connected components are called the C component. So for a given variable, you can look at the connected component of that variable, and I'll denote by Cx. Now the Tian-Pearl criteria says that a variable is satisfy Tian-Pearl criteria if no child of x belongs to Cx. So if I'm looking at x and I have this connected components, and I look at all the children, if all children are in different connected component than Cx, then I'll say that the variable meets the Tian-Pearl criteria. And the nice theorem Tian and Pearl proved is that for any variable x and for any value p v do x is identifiable if and only if x satisfies Tian-Pearl criteria. So it completely characterizes for atomic interventions when can you identify it, and of course they also give a very nice expression to write this. And again, the main focus was identifying this and giving this expression. So conditional properties of, or all the possible probabilities of observables assume are known. So here is an example of that particular graph we talked about. Now in the previous version of this, we had a u, but now I removed that u and connected x and y. Okay, so this is identical to the graph where that bidirectional edge you put split and put a u there. Okay, so in this graph, the C components are x, y is in one component and z is in another component. Now I'm looking at the intervention of x. So if I look at intervention of x, look at this children, it is z, and which is in a different C component. So it does meet Tian-Pearl criteria, and you can use the expression given in their paper to write down this beautiful conditional probability expression for the interventional probability. Okay. So that's the example. So I'm not going to go detail into how we write this, and that needs another set of definitions and all those things. But so far, I hope the theme is clear here, and I'm closing on the main theorem here. So what we did is that, okay, so we looked at those graphs which are, in the atomic intervention, and for those graphs where you can the Tian-Pearl criteria is met, and trying to, so Tian-Pearl gives the expression or probability expression, etc., for the intervention distribution. Now trying to make it so you wanted to get hold of this thing. So in other words, we wanted to learn this. So the theorem says is that it's there is an algorithm which takes this causal graph and variable, and suppose that it meets Tian-Pearl criteria, then you can actually output a representation of the distribution p hat, so that p hat and intervention px, interventional distribution, are epsilon close in its statistical distance. And now I from the first slide, I have all this timing fixed here. So computing, so you have a representation of p hat, you can actually evaluate that in time order n cardinality sigma kd plus k. So now I have introduced all these new variables here, not new, so k is the largest C component size, d is the max in degree of the graph, and sigma is the alphabet of the distribution. And you can also use this representation to get independent samples of p hat. And the algorithm, the learning algorithm which outputs this will take actually exponential in k and d, but it's linear in n. So typically, if I assume k, d, etc. are constant, then it gives you n by epsilon square. and similarly, so that is the number of samples required, and the number of the time complexity is similarly, but n square by epsilon square. Now there is a term, there is a variable here alpha. So notice that alpha represents the number of samples you need to take to find a certain specific joint distribution. Okay, so I'm not going to go into detail what that alpha is, but so we actually show that this alpha is required. In other words, you can come up with the lower bounds where it depends on alpha. Okay, so again, I haven't told what alpha is, but it is a parameter related to the sampling, how much samples you require to find certain event. Yeah, so that's the main theorem. Now I have one more slide. That slide is actually just show you how do we go about showing this. So we again use crucially drawn Tian-Pearl algorithm. Actually, their paper actually gives a way of writing this the CBN as a base net without hidden variable, so that the observational distributions are the same. So we kind of use that, and once we do, when we convert that, in degree of the original base, original CBN is D, and if the C components are at most K, then the in degree of the new base net becomes K times D plus 1. And then we use a learning algorithm, which is also very recent, which learns the base net. So what that says is that you given a specific graph, you know the graph, but you don't know the base, the distribution on the graph, but you can get samples from that. And then what this algorithm says is that actually you can output another base net on the same graph, which is very close to the original distribution. And that algorithm is going to take n by epsilon square samples, and I think n square by epsilon square time. So we use that. Of course, there are a lot of details here. In particular, even though we are converting the base net of the what we really of the original CBN, what we really want is the interventional distribution. Then you have to again manipulate that a little bit to get the interventional distribution, representation for the interventional distribution. So in the end, we don't completely learn a base net for the interventional distribution, but some other base net and if you marginalize with respect to X, you'll get the interventional distribution. And I think that's all I have to say. So as I mentioned, I didn't give a lot of details of the technicalities, but I hope I was able to convey the significance of the result. All right, thank you.
Okay, thank you, Vinod. So I think we have time for some questions.
Yeah. Oh, this is Jonathan Smith. I had a question about where you only assume 2 children from any given hidden variable. You know, you said it was standard. What's the idea there? If you have a hidden variable with more children, you just clone the variable and then spread the children out amongst those. But then that would seem it would change that graph, change the components in that graph that you made then.
I see. Okay, I should say I haven't thought about how to do that. I just assumed that it is possible. So you're saying that if I have multiple edges, you can just clone it and...
Well, that was my initial thought, but then it would seem that would change that notion of C component.
Yeah. So yeah, so I should yeah, and probably I don't know exactly how to do it. It should, yeah.
But, so when you say it's standard, this is just everybody just does?
Yeah, yeah. Every paper, I mean, the papers I looked at, they assume this. So,
okay.
yeah, that's right. So
okay,
I haven't
I
thought.
guess this is Jim Tian. I guess I can answer this question.
Yeah, very good.
You have multiple children. It's essentially you assume they are all in the same C component. So basically it has been shown that you can convert a graph with a hidden variable with multiple children into a graph with a hidden variable with 2 children, such that it will not change the identifiability results.
Okay, thank you.
Equivalent. The original graph is equivalent to the converged projected graph from the point of view of identification. So that has been shown to be the case.
Okay, thank you.
Thank you.
Any other questions?
Right. Shall I stop sharing or?
Maybe we can just leave it for a few more minutes if
Sure.
someone wants to go back to the slides.
Vinod, a quick question.
Yep.
Yeah, so at the very end, you shown there exists an algorithm that achieves certain sample complexity, right? And evaluation of sample complexity. So I don't exactly know the difference between the two, but basically you have some bound on these metrics. But is there any lower bound that you know? So just I'm curious how good.
Good question. So you know, the order n by epsilon square should be provable, like in terms of samples, because even to learn the base net, you will need there are lower bounds which require n by epsilon square to epsilon approximate a base net.
Okay, so lower bound is still n square, right?
No. So in the sample complexity, omega n by n square. So the main parameters n and epsilon. Sorry, n by epsilon square. What did I say? Omega n by epsilon square. Lower bound is known. So the dependency of alpha, sigma, etc. is not completely clear, but
I see.
So if alpha were constant, all those things, then yeah, then there is this lower bound of n by epsilon. N by epsilon square is known. Omega n by epsilon square.
I see. All right, thank you.
Yep. So that's in general, it is true that if I wanted to learn a distribution, base net distribution, it takes, if I wanted epsilon approximate, then it'll take, it needs n by epsilon square.
And most people care about, most people only care about the dependence on epsilon, right? So
yeah, that's right. So epsilon square dependency is 1 over epsilon square dependency is needed.
I see. Thank you.
So, any other questions? So if not, let's thank Vinod. Thank you, Vinod, for the nice talk.
Thank you.
So I guess we'll see you all next week.
All right.